And now, without any further ado, I would like to welcome, and then please join me to welcome together, Dr. Gavin Wood.
Thank you. Okay. Thank you. Yes, as Obi says, this is the sixth in this little tour that I'm doing to try to help people understand better jam. Welcome. The presentation that I'm giving is evolving all the time. There are some extra slides in this one, and I hope it will provide a better explanation than the last five that I've done, at least a little better. I'm going to start with some context for where Jam's design is coming from and where this general industry, I suppose, began, what's going on with it. What we're seeing these days is a sort of fork, a bifurcation in the industry, a divide. When there was only Bitcoin, we saw a presumption and a preponderance of long-term thinking, what these systems were meant to do, what blockchains were meant to do. But as time has gone on, a lot of these principles that Bitcoin proposed and started with have kind of gotten a little frayed at the edges, and we've seen teams in particular really pushing short-term results above the principles that Bitcoin set forth. I call these sort of long-term thinking, right? These principles. We want scalable decentralization. This is just the sensible direction to be going in. We know that blockchains don't scale very well, and so we need to increase this, but without succumbing to centralization. We know we need light clients, right? We know that RPCs are just not they're a weak point in how applications work. We need bridges that are secure, ideally trustless. We need to ensure that the fundamentals of the economics are sensible, are reasonable. And what we see is increasingly short-term results getting the better of some of the teams, some of the very well-known teams in the industry. We see small validator sets in order to manage higher performance networks. We see high-powered nodes, expensive nodes, very high barriers to entry. We see multi-sigs rather than secure bridges. We see very unreasonable and unsustainable economic basis for some of these tokens. We see, for example, blind signing. I've emboldened that one because it's quite poignant of late with the $1.5 billion hack that happened because of blind signing. This should be a wake-up call. We cannot put short-term results ahead of the principles, ahead of the foundations that Bitcoin showed us initially. These four words are not the same. There is some confusion that we sometimes see between these terms. Cryptocurrency can be considered to be sort of a virtual resource. A blockchain is a technology generally used for implementing this virtual resource, amongst other things. DeFi is a particular application vertical, a use case for blockchain, for this technology. Web3 is the broad approach, the thing that sets out what makes these systems different to the systems that came before. How we generally approach creating a solution, right? It's a much richer and more abstract thing than these other three. So what is Web3? You can think of Web3 as the basis for building resilient public digital infrastructure. So the key difference between Web 2, and for that matter, everything that went before Web 3 and Web 3, is resilience. It's about making these systems resilient. Resilient to all sorts of different things, but ultimately resilient. So it's a change, it's a fundamental change in the way that we would interact with the world and with each other because of that. So what is the resource of Web3? Well, Web3 could be considered to be multiple different things, of which multiple different technologies, of which one is blockchain. But if we think about the resource of at least blockchain, then we would say it's block space. It's essentially decentralized computation or secure, resilient computation. Now, computation involves a few different things. It involves, for example, decentralized execution, but you also have to feed data into the execution. So we need some sort of storage, data availability, if we're thinking longer term. And the means by which block space is delivered has a few different metrics by which we can measure how good it is. Block spaces are not all of the same quality. There is some block spaces which are of distinctly lesser quality than others. Now, if we go to blockchain, what is blockchain? Well, blockchain is really just a decentralized computer. Yeah, you can think of that. Think of blockchain as just a decentralized computer. Now, it's a bit of a funny thing to say a decentralized computer. Like, what does that mean? Computers, by their very nature, are particular things. Here is my laptop. This is a computer. It's not decentralized. It's very centralized. There's one of them, and it's right here. It's not over there. So what does it mean when we say a decentralized computer? How do we decentralize a computer? Well, in essence, we are going to mathematically model what a computer does and create or instantiate or manifest that model without there being a specific physical representation of it. And that's really what we mean by decentralization. It's a little bit like a virtual machine, a virtual computer. But with the key difference that most virtual computers pre-Web 3, well, all of them pre-Web 3, would have existed canonically in one machine. Like, if I run a Parallels or some other VM on this laptop, well, although it's the virtual machine, maybe I'm running, I don't know, Windows inside of it, but they're still effectively centralized because there's only one instance and it's on this laptop. Yeah. So decentralization, in essence, means not having just one canonical instance of something. So we find, if we look throughout history, that when we bring new technology into when new technology comes into the world, it begins as something very domain specific. There is a problem, and we create technology to fix that problem. And then usually, over time, it becomes realized that the technology can be used to fix other problems as well. And rather than just always building a domain-specific solution, instead what we do is we build general technology. We generalize the technology. Yeah? And by generalizing, we can use the same solution for different problems. And this is just a sensible way of doing it. We get economics of scale. Yeah? Over time, through the generality that we've now asserted, we can effectively commoditize the technology. And we just see this happening. It's a cycle. It's like technology gets invented, technology gets generalized, technology gets commoditized. And commoditization essentially just means being able to pay for that general technology from any vendor. Yeah, we become vendor neutral. We see this with general computation. We see it everywhere else as well, but I use general computation because it's kind of interesting because blockchain also provides computation. And early blockchains indeed were very domain specific. Bitcoin, right, was a very domain specific decentralized computer. It had basically one job, which was to mimic a currency. And then over time, we see this same solution being reused for other problems. Namecoin was an interesting early one, which allowed a decentralized name registry using a blockchain, but again, domain specific. Ethereum attempted to create something which was much less domain specific, much more general, and to some extent succeeded, but still not general enough that we can run regular software on it. Right? It still has domain-specific languages, a domain-specific instruction set architecture. Yeah? Over time, we will generalize further, and eventually we will hit the commoditization phase, where the block space we are buying will be essentially vendor neutral, will be interchangeable. We're not there yet, but we will get there. So Bitcoin, as I say, was a very domain-specific decentralized computer, very domain-specific blockchain. And Ethereum tried to generalize that and made some substantial steps in that direction. Polkadot is in the process of generalizing further and of increasing the amount of this resource, block space, to the point where we can reasonably start thinking of it as being commoditized. So Polkadot is designed already to create the highest quality block space. It's already the fastest by transactions per second, if you care about that metric. It's an imperfect metric. Many different vendors use many different meanings for what constitutes a transaction. Some vendors allow for transactions that don't have signatures. Some vendors allow for transactions that combine multiple outputs with only one input and count basically the number of outputs. But nonetheless, we are at the point of being an order of magnitude higher. We also have the highest bandwidth, the highest data bandwidth, even compared to domain-specific solutions for providing data availability, right? By far, Polkadot is the most decentralized of any of the major networks in terms of the number of economically independent entities that are maintaining its nodes. Polkadot, you would have to coerce or hack 149 such entities in order to compromise the network, which is substantially more than the next contender. And compared to Ethereum, Ethereum's not even on this chart because it's so low. Ethereum, I think at the moment, is at 3. At one point it was 2. Yeah? Highly centralized. Polkadot's also the most energy efficient. It doesn't cost much to run Polkadot in terms of energy. There's a reason that this number is so low, and it's not just our coding prowess. Polkadot scales out. It uses many cheaper nodes, many cheaper and more energy efficient machines, as opposed to some of these other networks which scale up, and they have very costly, very energy inefficient servers to run their network. So how does Polkadot manage this? Well, in large part, parallelization, or distributing its workload across many computers, rather than just trying to make one or two machines go really, really, really fast. This is done through data and execution sharding. Polkadot also manages it through shared security. Which is essentially the ability to allow many different economies to come together and share their security costs. In order to deliver an effective large system, Polkadot's been pioneering in interoperability, and in particular, languages which allow the different parts of Polkadot, the different constituent chains of Polkadot, the different shards of Polkadot to interoperate. Only through a common language can this happen easily. And of course, Polkadot's pioneered data availability, which is why that number is so much higher. Okay, so I mentioned before that Polkadot was building a Web3 cloud as opposed to a calculator or a computer. How do you build a cloud? Well, to build a cloud, a cloud is basically just a lot of computers. Ideally, the way you can scale them elastically, so you can add more in as you need more. To begin building a cloud, you really need some sort of fast computer, a supercomputer ideally. And then you need to be able to add more supercomputers if the initial resources of that supercomputer become saturated. So this is really what we are aiming for. Now, Polkadot was Polkadot 1, I should say, was a first step towards this cloud. The technology behind it could be used reasonably well, delivered very high amounts of computation compared to its peers. But it won't be enough to build a proper cloud. And that's where Jam comes in. So Jam is the latest technical specification that Polkadot is building towards. It's specified in the grey paper. It's going to increase the performance of Polkadot substantially. And in principle allow for it to be scaled even beyond the initial singular instance of this network. It's being implemented by many different teams who are totally independent of me, of the Web3 Foundation, of Parity, just totally independent individuals who are coming into the Jam ecosystem in order to try to create this decentralized computer. So as I said, it's based on the grey paper. Here's a copy of the grey paper. The grey paper is similar in format to the yellow paper, the Ethereum technical specification. It's a bit bigger. I think at the moment it's about 65 or 70 pages, whereas the yellow paper I think at the moment is about 45 or 50. It uses some of the same constructs as the yellow paper, so anyone who's familiar with the yellow paper should be fairly able to get into the grey paper without too much trouble. Crucially, by publishing the grey paper first, we don't create a reference implementation, and we really try to avoid falling into the trap of there being one implementation which is better than all the others and which therefore all the validators run, reducing the network's diversity and increasing its fragility. By basing the protocol on a particular definition, mathematical definition, we avoid this possibility, or at least reduce its chance of happening. There's a fairly substantial prize pool for teams who are implementing Jam of 10 million DOT. This is shared out between teams that get to the point of being able to provide a viable implementation. It's actually 5 milestones, with the first one being a very basic full node that doesn't have to go very fast, and the final one being a very fast, secure, fully functional validator node. There's additional support given to these teams. These are going to be the lifeblood of Jam and Polkadot's future protocol experts. So we give them, for example, on-chain salaries in stablecoins. We provide them with a fellowship sponsorship so that they can have some say in how the network, how the protocol evolves over time. We give their software professional audits, invite them to seminars, provide them with hardware so they can test their nodes, and also give them access to the Jam toaster. There are 36 teams at present that have declared that they are building Jam. And there are over 15 different programming languages used by these teams. So what is the toaster? One of the problems that you get when you're building these very large, distributed, decentralized systems is an inability to look very easily into the emergent effects. So if the system doesn't go as fast as you expect or has some problems, maybe it stalls sometimes, it's very hard to understand why, because it's not a single computer program or a single machine that is causing this. It's the emergent effect of 1,000 different machines, each running different software, potentially with different configurations. It becomes very difficult to track these problems down and optimize. Now you can run testnets, but testnets, if they are of the size of a large, the full network, the full production network, it becomes very, very expensive. You can also try to do the debugging on the production network, but the thing is, oftentimes you don't know who the validators are. And even when you do, they don't necessarily want to run your logging software or provide you with the outputs, because they may be very cautious with their, for example, their secrets, their keys. This has proven to be a bit of a difficulty within Polkadot. It's a difficulty that we're slowly overcoming, but with Jam, we're not going to make that same mistake. So with Jam, we're building the toaster. The Jam toaster is a purpose-built minor supercomputer. It has 16,500 AMD Threadripper cores, the latest ones running at 5 gigahertz or so, 32 terabytes of RAM, 16 gigabytes of just L2 cache, 20 petabytes of secondary storage. Right? It's a pretty decent computer. It's not going to compete with today's GPU supercomputers, but it is able to run a full-scale Jam network. And because it's all in one place, we're able to very efficiently take all the logging in real time and do deep analysis and experimentation on it, on the emergent effects from running the same software on 1,000 nodes, running different software on 1,000 nodes, introducing problems into the networking and seeing what happens, making some of the nodes malicious and seeing what happens. Really just experimenting and investigating the emergent effects of this highly distributed decentralized system. All right. So I've talked about the approach. I'm going to try and now explain to you what Jam is itself. There's a little picture of Jam that I did. It looks a bit like a flower. So let's go back to some of the driving factors of blockchains. What do we want to accomplish when we are engineering blockchains for Web3? Well, the first thing is it needs to be resilient, not fragile. Yeah? If a blockchain goes down 4 or 5 times a year, that's fragile, right? That's not Web3. That's not resilient. Bitcoin demonstrated that resilient public infrastructure can be built, right? Resilient digital systems which stay up even in so-called the wild. But Bitcoin wasn't general. Ethereum tried to push not just resilience, but also generality. So Ethereum tried to bring, with its technology, generality to the table. And to some extent it managed. That's a bit arguable, but to some extent it managed. What it didn't manage was performance. Right? It wasn't scalable. It didn't go very fast. It still doesn't. Polkadot managed to get the top three. Right? Polkadot brought performance, scalability to the table. But in doing so, there was a notable trade-off: coherency. Now, coherency wasn't something that was particularly widely considered at the time. How did Polkadot trade off coherency? Well, it has many parachains. And those parachains, those L2 blockchains, if you like, are all independent of each other. They all just do their own thing without regards to each other. Now, they can message each other, but those messages are quite slow and they're asynchronous. There is no atomicity, at least not inherently as part of the protocol, between the different parachains. Right? If you want to do a flash loan on one parachain and use it on a second parachain for a DEX transaction, that's not possible. So with Polkadot, we sacrificed coherency. Now, this isn't something specific to Polkadot. Cosmos does exactly the same. Ethereum, with its native rollups now, and prior with its L2 rollup strategy, also did the same. It's a pretty standard way of gaining scale, to sacrifice coherency. The question is, how do you sacrifice coherency? So if we look to the past networks, Ethereum, unscalable. Okay, we get that. Okay, look, what if we just, make the nodes closer together, give them really high bandwidth and really beefy memory, 256 gigabytes, and we don't care about being able to synchronize from the history, and we give them all fat CPUs. What then? Okay, well now you're basically describing Solana, right? This is a highly centralized, high-performance, synchronous blockchain. It's essentially scaled up Ethereum. There's a few tricks that are used, but in essence, what we're talking about is scaling up. What we find with scaling up is it tends to be centralizing. It tends to be very centralizing for a good reason, which I'll come to. It tends to result in fragility. There's a few reasons why it results in fragility. One of them is it's centralized, and therefore there are greater there is a greater emphasis on the points of failure. But another one is that they tend to be very software-oriented systems. And the way that you make software-oriented systems go faster is you optimize them. But optimizations can often have unintended side effects. One of the big reasons that Solana came down not that long ago was due to a software bug. Solana's not a protocol-oriented project. It's a very much software-oriented project. As the engineers make the software go faster, the issue is that the protocol essentially becomes fragile or insecure. Ultimately, such systems are not scalable. We know this. It's an adage, age-old in Silicon Valley. Scale out, not up. Yeah? If you scale a system up, you will ultimately run into the ceiling of what hardware can do. The ultimate endpoint with this strategy is to simply have a single computer that has lots of CPU cores and lots of memory, yeah, and you just run all the transactions through that single computer. Well, it should be very clear that's not Web3. That's not going to be resilient in the same way that like Bitcoin is resilient. So what else do we have? Well, some of the past work would be Cosmos. The idea that, well, okay, if one chain gets saturated with transactions, let's just add another chain and then allow the two to talk. The main problem with this approach is that it's insecure. The system as a whole, assuming that there is some sort of causality between these chains, will only be as secure as the weakest chain. Yeah, because the weak chain can always be compromised and have a message sent to the stronger chain telling it to do something that it shouldn't do. Or you can always do a reversion attack. Revert the weak chain after the strong chain has already done something. And then what happens? We don't know. the funds may be spent twice. Now, it also suffers from what I call persistent state partition. Now, this is, again, what I've talked about with Polkadot, essentially having silos of state. If an application lives on one chain, it cannot interact to the same extent with another chain. It's easier to interact with other things in your silo than it is to interact with things outside of your silo. And this is a fundamental issue for a few reasons I want to talk about in a second. There are high barriers to entry as well with building chains as opposed to building smart contracts. Deploying a chain costs more. You have to run nodes for a chain. In general, chains are going to be more complex. What about Ethereum? Well, Ethereum, this is slightly out of date now, but okay. Since Ethereum kind of changed its roadmap in the last month. But again, but at least until a few weeks ago, the assumed strategy of Ethereum was to essentially scale out through rollups, L2 rollups, from various different vendors. And these rollups would essentially scale the correctness that Ethereum gives its own smart contracts with what are called sort of rollup technologies, of which two are optimistic rollups and ZK rollups. Now, the problem with using lots of different technologies from lots of different vendors means that you get a very patchy sort of scale up, right? You get a patchy system. One rollup might have some particular version of the EVM, another one might have a different version of the EVM. One might like messages in one particular format, another in a different particular format. One might have particular latency and security characteristics, the others may have something else. You also get a degree of centralization, particularly from ZK rollups. Sequences for ZK rollups tend to require pretty hefty GPU supercomputers, and the economics are generally winner takes all, which means it's not much point having, or it's difficult to incentivize any more than one big player to actually bother generating ZK proofs and therefore sequencing. But the problem that I want to highlight with this, and it's the same with the current Ethereum roadmap of native rollups, is persistent state partitioning. Again, we're forcing state into these silos. And once you're in one silo, you're not in another silo. And this has important consequences, in particular atomicity. So we can talk about Polkadot, the relay chain, the parachain. Well, we managed to fix the first issue with Ethereum plus L2s, this patchy environment that people have to deal with. But ultimately, we still have a persistent state partitioning. And there are some higher barriers to entry as well with launching your own chain. So why do we have persistent state partitioning if it's such a bad thing? Well, it turns out that there is a physical constant in all of this. It's an antagonism that runs basically to the very heart of the universe, which is size synchrony antagonism or size coherency antagonism. And it basically means as a system scales, as a system gets bigger, and it can be any system, biological systems, physical systems, chemical systems, you name it. It reduces its ability to stay coherent for any given speed of cause and effect. Now, the reason for this is essentially the speed of light. Right? The fact that there is a speed of light implies there is a speed for fundamental cause and effect. And all systems will ultimately have some sort of physicality about them, some sort of distance between their independent parts of state, whether it's the distance between two transistors in memory, or it's the distance between two atoms, or it's the distance between two chemical constituents, or the distance between two cells. There will always be some sort of distance. And as systems scale, as they're basically able to process more things and hold more state, the distances between the atoms of state increase. Now, they do more than increase. We get an increase in the mean of the distances, but we also get an increase in the overall variance of the distances. As a system scales, the variances increase. So they get overall farther away from each other, but also some things get more farther away than other things. And this is where this is obviously a problem. It's a problem in CPU design, for example, and it's managed to some extent by having really odd circuit layouts where you will make particular connections actually longer than they need to be and therefore slower than they need to be in order to give overall coherence. But it gives opportunity as well, because it means that you can scale a system, and if you can just make sure that the things that need to have fast cause and effect are near each other, then you can have the benefits of a small system, but the scale of a large system. So here's a system. This is a visual language, visual representation of a smart contract system. Actually, it's more like an actor system. Now you'll notice a few things. Firstly, there's a border. That border is meant to indicate the shared state of this system. And there are arrows running down. The arrows are meant to indicate essentially the lifetime of these actors, right? Their runtime. So the actors are proceeding, they're executing, and the fact that they're in the shared state means that they can atomically interact with each other as they need. Now what we really want is to be able to add as many arrows as we want. Yeah? You can think of arrows essentially as like smart contracts or actors, but with continuously running. So there's no restriction on like gas limits or anything, right? We want them just to be normal pieces of software. You could also liken this a little bit to, for example, an operator, a regular machine, and these would be the software processes. When you open an application, you get another arrow, and it sort of just runs. Yeah. So if we try and fit Ethereum into this visual language, what do we get? Well, Ethereum has smart contracts. They don't run for very long. In my estimation, I think even if you have the most difficult possible block or difficult possible set of transactions, it will still only use about a second of computation out of the 15 that Ethereum has for its block period. And the rest of the time, Ethereum will basically be idle, right? And that's if it's the most difficult amount of or series of transactions. Most of the time it can, and on not such a great computer, most of the time it's even less. And what we see is that these transactions, or the smart contracts, sort of run for a little while and then they stop, and then another smart contract runs for a little while and then it stops, and so on. So in essence, this arrow is sort of being passed around between the smart contracts. And then there's a big period where it's just not doing anything, and then it starts again on the next block. Yeah? And we can sort of imagine this is more or less how Ethereum works. Now, the fact that the arrows sort of pass between each other means we can actually simplify this a little bit and just say, well, there's actually only one arrow. Yeah? It's single-threaded. Yeah? It might have different sort of processes, software processes, smart contracts, but in reality, only one runs at once, and therefore it's just one arrow. Yep. I mean, the two are equivalent, but conceptually. Now, if we try and optimize this, we might, for example, be able to shorten this period of idleness, yeah, between the blocks. We can basically fit more computation into each block. And we might even be able to do lots of things within we might even be able to do more computation within the smart contracts. For example, some blockchains are starting to try to use multiple cores on the same CPU, and therefore effectively getting a little bit of increase in the amount of computation that they can get through. Because it's all on the same CPU, I'm not going to try and draw like multiple arrows because that complicates the visual language, but I will make the arrow thicker to sort of denote the fact that it's able to use the CPU resources better. As I say, these generally trade the principles of Web3 in order to get performance. So what did Cosmos do? Well, Cosmos said, right, well, rather than just having one blockchain, let's have a few different blockchains and then use a bridge to connect them, or use many bridges. I mean, there's quite a few deploying a new Cosmos blockchain doesn't really cost anything other than your own time. It's not going to be secure, obviously, and it could easily just be totally centralized, but it doesn't cost anything specifically. You bring your own security to the table, and then you can maybe put a bridge. Bridging will potentially cost something because you'll have to actually get the other blockchain to accept its end of the bridge. The problem with it, of course, is that decentralization in this case comes at the cost of division of security. Yeah? And this is just a really terrible idea. You don't want to divide your security. That's the last thing you want to divide. So, okay, in this visual language, let's look at Polkadot, Polkadot 1. So Polkadot is a more sort of complicated thing. So we still have our single state, so it's a single blockchain, single security apparatus. But the state is partitioned, right? That's what these 3 lines are for. And then we have per block execution. So we start, and then we stop, and then we start again. And then we also have message passing, which happens inside of this, secure message passing. Message passing actually happens inside of this overall system. And this is probably, I mean, you know, it's always hard to read the minds of the Ethereum folk, but probably something not too different to what Ethereum is attempting to target for the end of the decade. So what's Jam? Well, in this visual language, this is how we might describe Jam. So on the right, we have our familiar blockchain system, right? Single-threaded, pretty much. And we run these arrows. They take, each one executes at once. But they're fed not from the outside world, but actually from another part of the system, the central part of the system here, which also has its own arrows, running at the same time, so in parallel to these arrows, but also to each other. And these arrows provide the inputs to these arrows. Now, the inputs for the bigger arrows come partly from the external world, but partly from this large storage facility. Now, the large storage facility is shared between these arrows. You'll notice the arrows are outside of this state. The arrows are stateless, right? This computation is stateless, except for the fact it can read and write to this large storage facility. When I say large, it's actually 1.5 petabytes. So it's a pretty substantial storage facility for blockchain. You'll notice that these arrows cross, in essence, signaling that what one arrow outputs takes a little while before it's available to the other arrows. These arrows are what we call cores, not CPU cores, but Jam cores, sort of virtual machine cores. They are the computation that gets distributed over the Jam network of nodes. 1,023 nodes gives enough room for 341 cores. The cores are fast. Now, if you don't want to pay this 1 second or this 1 block latency, then you can keep your work on the same core, and it will automatically have access to the same data that your previous workload calculated. This is what we call core affinity, and it's something you have the similar thing in CPU design. Basically, each CPU core has a cache, and that cache, as long as you're using the data in the cache, it's fast. But if you're using data that's in some other core's cache, everything has to synchronize, and it has to sort of go to flush it out to main memory, and then re-import it into the using core's cache, and that takes time, right? It stalls, essentially. And Jam has exactly the same design. Yeah, it's not that the data is like missing, it's just that it stalls until the data becomes available, which generally takes a few seconds. So, JAM introduces the core model. JAM is a chain which is generally coherent, but with transient decoherence. It becomes decoherent for a limited period of time, basically for 6 seconds. And at the end of those 6-second periods, it becomes coherent again. The computation model is split between what we call in-core, which is stateless but has access to that dynamic, that distributed decentralized data store, which we call a D3L, the distributed decentralized data lake, on the one hand, and then on-chain, which is synchronous, fully coherent, and stateful. So it has 2 execution paradigms that are fundamentally connected. This data lake has 1.6 petabytes, and as I mentioned, it's got this inter-core synchronization latency of 6 seconds. There's also a data lookup for essentially giving these cores a piece of sort of firmware, so that if data is in the firmware, they can just read it fast and cheap. All nodes store data in the firmware, so it's always available. And JAM provides this. So if you're basically just going to keep wanting to read the same data block after block after block, you don't even have to use the data lake. You can just put the sort of data in the so-called sort of virtual firmware. Now the data lake stores data in segments, fixed size segments, via a cryptographic commitment. So when you want to read from the data lake, you get given this sort of 36-byte identifier. And it will give you back a 4 kilobyte segment. Yeah, 4 kilobyte segment. The 4 kilobytes is an interesting size because it also happens to be the size of memory pages on regular, like typical CPUs, typical regular silicon CPUs. We'll come back to that in a second. Now, if we want to rephrase all of this in more Ethereum terms, then we can say, well, actually, JAM has 341 Turing complete. I put it in quotes because, of course, it's not really Turing complete because we have gas limits. Yeah, we have block gas limits. But those gas limits are very high for JAM, stateless rollups. We also have 1 Turing complete sort of smart contract chain, right, that can combine the effects of these stateless rollups. Rollups have a common access to a 1.6 petabyte, the A store, synchronized with 6-second latency. And if you happen to be running work on the same core, block after block after block, then that latency reduces to 0. You can instantly access any of the data that you previously computed. How do we achieve this? Well, we have what I tend to call cynical rollups. I don't believe in the term optimistic rollups. I think it's just a great piece of marketing. I would call them pessimistic rollups because they take a very pessimistic view of what might happen. They assume the worst. So they assume there is some problem, some fraud, and they wait for however long, half an hour or 4 days, in order for someone to prove that there is fraud. And only if that time passes do they then accept that it's probably fine and actually allow there to be effects coming from that work. That's very pessimistic. Waiting 4 days on the chance that there might be some fraud proof that's going to come after 3 days and 23 hours is a very pessimistic attitude. We have cynical rollups. I like the difference between cynical and pessimistic. We're not pessimistic, but we are cynical. We assume that there is going to be, or that there could be, some fraud, and therefore we do everything that we can to check whether there is fraud. Actively, not passively, actively. And by actively checking this, by using our validators to actively check it, we're able to deliver fast finality across hundreds of different rollups cheaply. We have a zero-knowledge proof-based block authoring system. The reason for using zero-knowledge proof in the block authoring system, it's called Safrol, is essentially to avoid giving away the identity of the next block producer before they produce a block. Why do we want to do this? It's all about avoiding fragility and creating resilience and security If the next block producer's identity IP address is known, they can be DOSed before they produce a block, and the chain can get stalled. Stalled for one block, maybe if they can see that there are, 3 blocks being produced by the same block producer in a row, they could stall it for 3 blocks. This is a problem. Some attacks rely on there being no on-chain activity for a period of time. It may only be a short period of time, but some attacks rely on this. This allows those attacks to happen. Now, some networks, notably Solana, disregard this consequence, just assume it will be fine. But this opens them up to these kinds of attacks. Now, if all you're using it for is, mad memes, then it doesn't really matter. But if you're using it for anything of any significance, any consequence, this isn't something that you want to build into your system. We also have near instant and adaptive finality. So adaptive is crucial. If network traffic goes up, network conditions deteriorate, we still want to gain finality, but we don't want to just be constantly getting 2/3 of the way through finality, and then a new block comes along, and then we disregard the previous thing and get 2/3 of the way through that, and then another block comes along, and always playing catch up, right? What we want is to essentially slow down the finality if the network conditions deteriorate, and speed it up if they're fast, if network conditions are good. And that's exactly what Grandpa affects. Yeah? So if network conditions are regular, Grandpa will finalize within a block or so. If network conditions are irregular, it will still finalize. It might be 2 or 3 blocks later than normal, but it will still finalize. It will always act in the optimal amount of finality latency. Finally, the technology, and one of the very important technologies that Jam brings along, is a new virtual machine, the PVM, Polkadot Virtual Machine. This is an incredibly fast recompilation-based architecture for describing software and getting it into x64 machine code. So it's not x64 machine code itself. This would be way too bloaty and come with all sorts of potential non-deterministic gotchas. Nor is it RISC-V, but what it allows for is to deploy software into it that was compiled for RISC-V, and then, just in time, just prior to software execution, recompile it into x64, and then run it essentially as native. Now, this is a big deal. This is a new thing for blockchain. Blockchains have tended to have highly domain-specific instruction set architectures. Polkadot was a trailblazer in using WebAssembly, which was much more general ISA. But WebAssembly is problematic. Aside from being increasingly complex, WebAssembly didn't allow for the possibility of, didn't allow for stack being placed in main memory. This made continuations in WebAssembly a real pain. So PVM. PVM is an instruction set architecture. It's based on RISC-V. If you don't know what RISC-V is, it's a very simple instruction set architecture devised by an academic and his team. It's the 5th in its series, and it has quite substantial industry support. So you actually can buy RISC-V CPUs, and there's RISC-V can be targeted by modern compilers for compiling your C, C++, Rust code into. So it's very general purpose. RISC-V can be recompiled into PVM very easily. We already have software for doing this. So you can write regular code like C++, Rust, whatever you want, and then use LLVM to compile it into RISC-V, and then use our little sort of bolt-on to LLVM to recompile it into PVM. PVM machine architecture has 13 64-bit registers, 4 kilobyte paged address space, 32-bit. It looks like a regular machine. Yeah, it looks like x64 on the sort of basis, on this sort of basis. The one slight difference with sort of typical modern architectures is it's Harvard architecture. So the code that executes is stored sort of separately in a sort of ROM, separately addressable ROM, to the RAM, right, to this 32-bit address space. This is mostly for security. Like, we don't want programs that are altering their own code. That would be a potential significant security risk. PVM can be recompiled in linear time, secure linear time, into x64 and ARM64, right? Now that linear time, it turns out, is very small, and you can't create compiler bombs. This is also one of the issues that we have with WebAssembly. If we want the best recompiler into x64 for WebAssembly, it's not linear time. People can create programs that will make the recompilation slow, and this is problematic for a permissionless system. We've managed to create an implementation of the PVM that can be dynamically metered with minimal overhead, about 10%. So it's only 10% slower to work out in a deterministic fashion how many steps it's taken. This is also a big deal. This is not something that we had with WebAssembly well, we didn't really have it at all. Because this is a regular machine, its stack is in main memory. This is also a really important thing. If you want to close the machine down and then at a later point spin the machine up again and have it continue where it left off, then you need for the stack to be in main memory, or you need some other way of saving it and some way of representing it, and this is a pain. So, but if it's in main memory, all you need to do is save all of the addressable pages of main memory and you're good. Yeah? When you want to spin the machine up again, you put the addressable pages back in their place and the machine will carry on as though nothing had happened in between. This is very helpful for doing what we want to do. We've got an implementation of the PVM that achieves 45% roughly of native x64 speed. So if you take the same software and you go through this RISC-V PVM x64 pipeline and you compare it to the same software that's just going directly to x64, we get 45% of the speed. This puts us in a position where we can reasonably start thinking about building regular software and deploying it on chain, because the chain goes not very differently at speed to a normal machine, a normal computer. Okay, so how do you interact with Jam? Right, well, there are services on Jam. Services are a bit like smart contracts. Yeah, not too much differences between services and smart contracts. There are a few important differences. One of them is that services have 3 entry points. The two are the important ones. This one isn't so important. Refine, which does all of the roll-up stuff. Refine is the code that executes in those big fat arrows in the middle. Accumulate is the code that makes it coherent again. And accumulate code happens in the arrows off to the right, the small arrows off to the right. There's also on transfer, which handles message passing between the services. So services are a bit like smart contracts, except the computation model is different. The computation model is staged, so the different stages, refine and accumulate, and on transfer. It's pipelined, which is to say that when refine is executing, the previous block's accumulate is also executing. Yeah? So it's parallelized in the sense of execution parallelism. And it's distributed, which means that when one refine from a service is running, that same service might have other refines running at the same time. Yeah? So a single service, or smart contract, can actually be sort of multi-threaded. It can have many refines running at the same time. But it's not really multi-threaded because it's not on the same CPU. It's distributed across a very large node network. In principle, one service could have 341 different refines all running at the same time. Yeah, that's why we say it's distributed. Unlike smart contract systems, you don't pay for a particular piece of transaction to happen. Instead, because the thing is, transactions are so small, it would start bogging the system down if we were to actually have to pay for 10,000 different transactions within a single block. So instead of doing this, what we do is we say, you just bulk purchase execution time or block space. And then it's up to you how you use it. And we push that problem off into the services themselves. This also switches the paradigm. Instead of being very sort of an obvious sort of Bitcoin evolution, right? An obvious sort of alteration on, a revision of Bitcoin, we're really moving into a more cloud-oriented paradigm where you buy significant pieces of computation. In Jam, initially, computation, like for Polkadot, is sold in 1 month segments. So you buy 1 month of computation on a Jam core. Now you can then split that 1 month all the way up into, I think, around, basically every different block. You can basically, for every different block, nominate a different, piece of work to be done. But in principle, that block space is purchased in bulk. And generally, Jam is asynchronous. What do I mean by this? Basically, services operate largely independently of each other. When they want to interact, they can read each other's state and they can send messages to each other, but that messaging is done asynchronously. Whereas on Ethereum, most smart contract platforms, messaging is synchronous. When you call into a smart contract, its code runs immediately, your code is suspended, and then when it returns, your code continues with any return data. All right, so Jam is permissionless, or at least it's designed to be permissionless. It doesn't actually have to be permissionless. Jam doesn't really care about this stuff, but it can be permissionless, and this is the important thing. So Jam hosts services, code and state and data. Introducing a new service is designed to be permissionless. It's designed so that anyone can do it, and even if they're malicious, they can't affect anyone else's services or how they run or how expensive they are. Services are limited only by deposit requirements, right? You have to deposit more tokens into the service. The service has to hold more tokens in order for you to have bigger code or data or state. But that's all. There are no artificial limits here. One example of a service could be the Polkadot 1 service, or securing L2s, right? Securing parachains. That would be an example of a Jam service. So as you can imagine, services are pretty powerful things. Jam doesn't care about this stuff. For Jam, this stuff is L2, right? This is like what services handle. Not staking, doesn't care about economics, doesn't care about governance. This is higher level concerns. So let's dive a bit deeper into the Jam pipeline. What's actually happening when Jam is doing stuff? So there are 3 main steps when work comes into Jam, when a transaction, so to speak, comes into Jam. The first step is authorization. We have to make sure that it's worth Jam's time to execute, to do this computation, right? This is looked after on Ethereum by having a gas price that you pay before the transaction starts executing, yeah? So you pay for some gas, and only if you can pay for the gas does the transaction execute. We don't do that because we're dealing with such huge amounts of compute that we can't split it up into that sort of small payment. So instead we authorize for like a whole core for 6 seconds. And that means basically running some code. So we pre-purchase our computation on Jam, and then we attach to that purchase, when we're ready to state what we want to use it for, we attach some code. We call that the authorizer code. It's totally independent of the service code. Yeah? And it is the purchaser that decides this. So by purchasing core time on Jam, by purchasing Jam block space, the thing that you get for your purchase is the ability to decide what the authorizer code is. And it's the authorizer code that runs on the input, on all the data, the transaction data, if you like, and make sure that transaction data is in line with what the purchaser wanted to happen. As the purchaser, you choose your code well in order to avoid your purchased core time or block space being used for the wrong kind of work. After it's been authorized, after we've decided, yes, it's good, it is what the person who purchased the core time wanted, or the sort of thing they wanted to do, then we move on and we run refine. Now refine is now into the service code, yeah? The smart contract code, if you like. It's the first half of the smart contract. And this uses the muscle of Jam. This uses one of its cores, yeah? Once the refine is completed, the output of refine is fed from the in-core environment into the on-chain environment, the stateful environment, where it has access to the definitive state of the world. It's still in the service code. And then we accumulate the effects into our state, into the services state, and therefore into the world state. So let's have a look at what data is flowing around Jam. We have items. These are essentially sort of transactions, transaction data, yeah? They're associated with a service. A bit like in Ethereum, when you send a transaction, you send some data into a smart contract, and you have to say which smart contract you want to send it to. It's like the address. In Jam, we associate with a service. In Jam, service addresses are 32-bit integers, not 32-byte hashes. We have the concept of a package. Package is basically a bunch of items with some authorization token. The authorization token is the thing that we pass into the authorizer to say, it's the real deal, let us through. It might contain a signature. That would make it quite similar to how smart contract chains like Ethereum work. But it might contain some ZK proof that the work being done is in line with what the purchaser wanted. It could contain whatever it is that you want. It's Turing complete. And then we have the concept of digests. Digests are what come out of refine. And again, they're associated with a service. Okay, so we have some transformations that happen. The first one is authorize. It has our package with our items in, and it translates it into what we call a trace, this thing. This is a trace. And basically it's some output from the authorizer that lets us know further on in refine and accumulate, like anything the authorizer wants us to know. It might let us know, for example, the identity of the packager. This would be potentially a quite useful thing. Maybe they want to give the packager a reward if it's something like a parachain. And we must remember that our package is really just an authorization or a token with some items. We then refine each item. Into the refine code, we pass an item and the trace. And refine gives us this digest. Notice it's labeled in red. Each of the different services have a different color. I've got 3 services going in this example. So the red service would be refined, and also the orange service would be refined, and the blue service would be refined. And you'd end up with an orange digest and a blue digest. Next, we get to the jam stage, the join and accumulate. First, we have to join together all of the digests that are for the same service. So, for example, we might have a work package like this one that has red, orange, and blue along with its trace. And then we might have another work package that has red and blue along with its trace. We might have several others, maybe that don't involve red at all. And we're going to turn that into the red digest with its trace and some other red digest with its trace, taking this one and this and this one and this. We only want the reds, yeah, for when we're running red accumulate. When we're running orange accumulate, we only want the oranges, and when we're running blue accumulate, we only want the blues. Yeah? So we group them together by color, by service. Yeah? And that's when we move into accumulate. Accumulate feeds in all of these digests of the same color into that color's accumulate code, that service's accumulate code. Yeah? And we end up with a hash. And the hash is the thing that we sort of can prove if we're on a light client bridge or something. But more importantly, this is stateful. We can alter our service's state. Let's dive a bit deeper. So, authorize. Authorize can inspect the entire package. Package includes a token, and the package is invalid if this code panics. That's how we invalidate a package. That's how we say this is not authorized. Just panic. And that invalidates it, no more work will be done. But assuming that the package is valid, then this authorizer will return a trace. Trace is just a bit of data, right? There's nothing, it's just opaque data. How do we associate a core with an authorizer? If we understand that an authorizer is a piece of code that can identify the sort of work we want this core to be doing, how do we attach that to a core that we've purchased? Well, every core has an authorizer pool and an authorizer queue. It's associated with that core, and it's maintained by Jam. The pool is replenished from the queue, right? And the queue is just a circular buffer, a ring buffer, right? So it just goes round and round and round, always replenishing into the pool. The pool is a fixed size. And if for some reason we have nothing to do on a core because there's no work that we can identify as being within the pool, then we just drop something from the pool, the oldest thing, and still replenish from the queue. Authorizers are arbitrary code that basically we give it a token and it gives us a trace, or panics. The arbitrary code is fx, right? What's the x? The x is parameterization. It turns out that oftentimes we want exactly the same authorizer logic, but we just want to parameterize it differently. For example, we might parameterize it with the account ID, and we just have a general signature authorizer that's looking for a correct signature. But we want to parameterize it with an account ID. We don't want to keep having to recompile code just with a different account ID. Yeah, we want to parameterize it so that we can reuse the same code, but just with a different account ID. And that's essentially what this X is. It's some parameter to the code. The commitment to this authorizer must be in the pool when it makes its way on the chain. And this is why it's not in anyone's interest to put forward a package that, although it might have a valid authorizer, that authorizer commitment isn't in the pool. Yeah, it's not meant for work for this particular core. And that's essentially what connects the purchaser of core time with the user of core time. Now, if they're the same person, it's fine. They just basically make this a signature and it's done. And this is how Ethereum works, right? The purchaser of gas of a transaction is generally the user of that gas of a transaction. It's the same thing. In fact, it's essentially enforced to be the same thing because the account ID which gets run is the same account ID whose gas, whose ether is drawn from to pay for the gas. Yeah, it's actually mandated by the protocol to be the same thing, the purchaser and the user. We don't want to do that in Jam because that's not what we can't do parachains very well if we enforce this equivalence. Parachains, really, we want the purchaser to be the parachain itself and the user to be whoever is the collator, the block builder for the parachain. They're two different people, potentially. So if we have this equivalence, we create massive complications for ourselves. Complications, I might add, that Ethereum is slowly trying to figure out by having one of the latest EIPs tries to kind of deal with this at a higher level and allows for the possibility of some at L2 for a transaction signer to not be the one who is actually running the actual smart contract, essentially trying to decouple these things that Ethereum coupled as part of its protocol. We avoid that already by having this system in place. Moving on to refine. So refine is performed on a single work item. It can look at the authorized output, which is that trace that I mentioned. It can inspect other items in the same package. This is a big deal. This allows for quite easy co-sequencing. Every item that's being done in a package can look at all the other items being done in the package. No data is siloed. It can make pre-image lookups, that sort of firmware thing I mentioned before, and also invoke PVMs. It can create new instances of the PVM and make them run. Yeah? This is a big deal. It can create new instances of the PVM. It can create new virtual machines with arbitrary contents in memory and run for an arbitrary amount of gas. I'll come back to that. Items have a maximum 12 megabytes of data that can either be totally external to the system, coming in as like transaction data, or be drawn from the data lake. Items can place up to 12 megabytes into the data lake. And this is a 6-second slice on one core, right? Multiply these numbers by 341 to get what you can do in Jam in every 6 seconds. Items can execute for up to about 5 seconds of PVM gas. And if you remember, PVM gas goes at about 40 to 50% of regular x64 speed. Yeah? So we're looking at between 2 and 2.5 seconds of x64 speed every 6 seconds of Jam. Every 6 seconds wall clock time, we get 2 to 2.5 seconds of real x64, this is actually Apple Silicon, but x64 CPU time. This is huge. Basically, Jam only introduces a slowdown factor of about 40%. Yeah? On what you can do on a regular machine. And Jam has 341 cores. It's starting to look a lot like a decent computer. Items yield up to 48 kilobytes in their digest, and it's this digest that then gets fed into the accumulate function. So accumulate is performed on one or more digests of a service. Yeah? If there are more than one, it can choose what to do with those digests. It can see them all at once and then order them as it chooses, or disregards them if it decides that they're mutually exclusive. It can inspect all of the traces of each digest. So it can go back and see what authorizer authorized each of the digests, well, each of the refinements to give each of the digests. Now, accumulate is fully synchronous, fully coherent, so we don't get that massive amount of compute muscle that we get with refine. Instead of the 5 seconds-ish of PVM gas, we only get 10 milliseconds of PVM gas. So it's a lot less gas, right? This is just because it's a synchronous system. Yeah? And if we have 341 of these that are potentially all in the same service and therefore all have to execute synchronously, we only have 6 seconds per block, and we need a bit of time for synchronizing all the nodes. So actually, 3.5 seconds for executing all of the accumulates is this leads us to 10 milliseconds of gas per digest. That's just the way it has to be. This might be able to be increased if there are different services. We assume for the moment that there could be the same service 341 times, and therefore the need to have total synchroneity. If we can guarantee, for example, that the maximum amount of the same service is only 170, then we could increase this to 20 milliseconds because the services are entirely designed to be able to execute in parallel for accumulate. Accumulate can transfer funds within the state of the chain, alter state, read other services state, create services, upgrade code, all of this stuff. Accumulate happens asynchronously to all the other services accumulate. This is what allows us potentially in the future to parallelize accumulate and increase that 10 milliseconds a bit. So any transfers are post, which is to say the transfer sort of gets queued and then executed after all of the accumulation is done. Whereas the foreign state reads are pre, which is to say the state that you see when you read other services will be the state that the service was in when you started executing. Yeah, when this batch started executing. All right, so that's Jam. I want to talk a little bit now about core play, which is basically why are we building Jam? Like, what's this for? It's Jam's signature service. And the first part of core play is already under development. To begin trying to explain core play, I first want to talk about why do we have more chains? What's the fundamental thing about having more chains? It's not specialization. Specialization can be helped by having separate chains, but that's not actually the fundamental reason. Nor is it sovereignty. Having each of the smart contract systems, if they are sufficiently powerful, can provide both specialization and sovereignty. In reality, it's scaling out. We have L2s solve the scaling out problem at the cost of persistent state partitioning, essentially at the cost of siloing. And what's the problem with having multiple L2s with siloing? Fragmentation. You've fragmented your ecosystem. You've fragmented your system. Yeah? It's harder to develop for. It's harder to get nice big economies on. What's the problem? Well, it limits network effects, right? It limits the use cases. It limits atomicity. You can't atomically combine different services. If you want to atomically combine a smart contract on OP stack with a smart contract on Arbitrum, good luck. Yeah? It's hard. It becomes very hard indeed. It limits developability. It's a lot harder to develop applications if you're developing it across multiple independent state systems, partitioned state. And if you're a team, it forces you to make a decision before you deploy without very good information. You don't know what the place that you deploy, the silo you deploy in, what it's going to be like in a year's time, 2 years' time. You don't know that landscape. You're effectively forced into this decision, and it's a very difficult decision to reverse. Let's go back to what it is that we wanted to achieve. Hopefully we'll get the picture. There it is. So this is the ideal situation. I mean, not specifically 9 arrows. We want the arrows to go on, indefinitely. But this is what we're really after. Now, there's a few things about this compared to the other systems that I mentioned. One of them is the arrows are continuous. They're not broken, right? We don't want to have to pack everything up every block, only to sort of have to restart again in the next block. This is a pain. Block gas limits are a pain. Yeah? We want lots of arrows, and we want them all in the same state space so that they can atomically combine whenever the application desires. So with Jam, that's not the same. That's not the end goal, right? The two look quite different. So why are we developing this? Well, it turns out Jam is a very useful stepping stone to get to core play. You can think of core play as a Jam service with a Jam L2, or alternatively as a smart contract operating system for Jam. Core play achieves, to some extent, to a much better extent than has been achieved thus far, the ideal situation of indefinitely executing, unbroken execution of actors or smart contracts able to atomically compose with each other whenever they want. How does it do it? Well, essentially, it uses dynamic partitioning, not static partitioning. So instead of forcing all of our smart contracts and services and so forth into one of a number of silos, one of a number of L2s, or one of a number of parachains, or one of a number of subnets, or whatever you want to call them, instead they all sit in the same shared data lake. And when we need to compose any particular subset of them, we bring in the state that we need, and we do the composition. They all go back to the data lake at the end. And in essence, we have avoided the need for persistent partitioning of state or persistent decoherence. So core play is a solution to scaling smart contracts without the fragmentation that we typically see in the current approaches. The smart contracts are actually better than smart contracts. Smart contracts are assumed to be transactive, which is to say they may have some state, but all of the interactions are fixed length in terms of computational steps. right? So the language of smart contracts is not Turing complete because we have to assume that essentially every function call into a smart contract is bounded, and it's actually quite severely bounded. It's bounded by the block gas limit. Yeah, the transaction has to have been finished. So any single operation on our smart contract has to have been finished in the Ethereum world within the block gas limit steps. If it gets to the point where you can't finish it in the block gas limit steps, your contract is screwed. It's bricked. Yeah? Core play allows for actor-based smart contracts. Smart contracts that just execute indefinitely. Regular software. If you want to put an infinite loop in there, you can. Yeah? These actor-based smart contracts are elastically scalable across cores. Yeah? So the contracts themselves are not, but core play, the environment is. So if you want more and more smart contracts to be in core play, you can. As state space grows, it just takes over more of Jam. Core play provides global atomicity, so any two smart contracts can atomically compose if they want, or indeed any 3 or 4 or whatever. The more smart contracts compose, the more expensive it's going to be, because the opportunity cost grows. And also, there is a limit to the number of smart contracts that can atomically compose, but it's quite high. It's essentially the amount, amount of work that you can get done on a single core, and still, or the amount of contracts whose work you can get done on a single core, or at least a portion of their work that you can get done on a single core. There is zero fragmentation. This is crucial. We're not siloing anymore. How do we do it? Well, we have this shared data storage system, the data lake, that Jam provides. We're pipelining a lot, and we have the PVM. PVM is crucial because it has the ability to support continuations, and it's so fast. We keep our state atoms small. We're not dealing with attempting to co-schedule blockchains. This is very problematic. By keeping it at the level of smart contracts or actors, we avoid the need to essentially bring together and co-sequence these huge systems. We repartition regularly. Yeah? So we're always switching these guys around. There'll be some that don't get repartitioned so often because actually it's economically optimal for them to always be co-sequenced together, right? There might be smart contracts that are sort of would have otherwise been on the same blockchain, yeah, sensibly. And we do economic efficient co-scheduling. So we're always on the lookout for opportunities of combining these small state atoms, these actors, whose atomic combined composition would give good economic output. So why don't we, what are alternatives to the sort of Jam paradigm? What about co-sequences? Co-sequences are a fair big sort of thing in Ethereum at the moment. To some extent, this is what Jam is doing, right? Jam is, in essence, a system that is designed for efficient co-sequencing. But that's the trick, you see, efficient co-sequencing. Co-sequencing blockchains, vast multi-gigabyte states, is crazy. In order to co-sequence blockchains, even just 2 blockchains, you're going to end up with a pretty big centralization bias. You have to be validating at the same time on both blockchains. You have to have a full block authoring node on both chains. You have to track opportunities for co-sequencing, which is more logic that has to be run. In the end, you're going to have like a pretty beefy machine to be able to do any sort of co-sequencing. Worse, you have to track entanglement. So entanglement is the concept of like cause and effect moving between chains. So something caused on one chain has an effect on another chain. Now, if you have entangled cause and effect or entangled chains, you have to ensure that both chains execute this entangled effect, either the 2 of them or neither of them. This is crucial. You can't just sort of put a transaction in that is entangled with another chain and just hope that they both get finalized. Yeah, hope that nothing mutually exclusive happens before they get integrated into the chain state. This is not, this is basically, we're down to insecure bridge territory. So in order to track entanglement, this becomes an order n squared issue, right? Now with 2 chains, it's not so bad. But if we wanted to scale this up, scale this out to like 300 chains, then every one of those 300 chains would have to be tracking what the other 299 are doing to ensure that any entangled effects in the other 299 are properly represented on this chain. Yeah? So that no entangled effects might happen on one chain, but not on another chain. All of the chains have to track all of the other chains. This becomes a big efficiency issue. Blockchains are too big to be co-sequencing sensibly unless we're willing to employ supercomputer sequencers, at which point we have huge centralization bias and it ceases to be resilient. What about intent solvers? Well, I mean, intent solvers are kind of interesting as an approach, but they fundamentally don't actually allow composition, right? They're essentially a way of abstracting multi-chain transactions. They're not a way of creating composed solutions across chains. What about multiple instances of the same contract on different chains? Well, you've already broken it because the different instances are totally independent. There's no network effects to be enjoyed. They also tend not to be generally applicable. Finally, why not ZK? Like ZK is pretty big at the moment. Why are we not using it? I mean, we are using it a little bit, right? Our block production mechanism uses ZK. But ZK is not at present cost effective to use, and certainly not green to use for scaling specifically. Yeah. In our most recent analysis of the available ZK technologies, which admittedly is like a little out of date now, it's about a year old, it cost about 2 million times the amount that it cost to do using our cryptoeconomic scaling system. Now that's probably gone down an order of magnitude over the last 12 months, maybe. I mean, I don't know for sure, but it's possible. But even still, it's way too expensive to consider using at this stage. It is something that we could consider using as ZK technology improves over the next 5 years or so. We'll see. Good, that's the end of the talk. I am going to dive into a little demo. So Jam is parity. So as I mentioned before, there's like 35, 36 teams implementing Jam protocol. Parity being one of them. I'm quite active in implementing it within Parity. And I want to show you a little bit of what we're doing here. Good. So here is I built a little REPL, little CLI for Jam. Before I get into the REPL, what I want to show you is what an authorizer looks like and what a service looks like in Jam. So I've talked you through what authorizers are, what they do, how they fit in. I want to show you some code. Can you all see that? Do I need to make it bigger? I can make it bigger if desired. I'll make it bigger. Okay. So this is an authorizer. As you can see, it only has one function. This is a sort of stuff on the outside. Here's the function, is authorized. It takes the parameterization, that little x in the subscript x, and it takes the work package to be authorized. And it basically either succeeds and provides a trace at the end, or it panics. The code specifically just says, let's print a debug string. So it's just going to print something out onto the debug log. And then it's going to check to see, this is the only check this authorizer does because it's just a simple authorizer, nothing particularly interesting going on. It checks to make sure that its parameterization data is equal to the authorization token. So you remember I said authorizers can be parameterized, so you can do the same kind of thing, but with a different parameterization. And then every work package has an authorization token, which the authorizer can use to make sure that it's legit, that it's using the core as intended. In this case, we're just checking that they're the same. If they are not the same, then we panic. Yeah? It's not authorized. Assuming that they are the same, then we're just going to turn this authorization, which is just regular data, into a string, like human readable, and we're going to output this little message, auth equals whatever the token was, and that becomes our trace. Yeah? Very, very simple. We're just checking that its parameterization is equal to the token and outputting the token with this little message. Let's have a look at the demo service. So, after a little bit of boilerplate, we have our service code. So this is a little bit more interesting. We have 3 functions. First one is refine. So if you remember, refine is the thing that runs on the really high performance cores. Yep. First, what we do is we take our authorization output, we fetch it, and we're calling that auth output. Okay, that's easy enough. This, if you remember from the null authorizer, is just going to be this something that looks a bit like this string. Yeah. And we're going to print a debug message. Easy enough. We're going to make a new message with describing our payload and our authorization output. That's calling that MSG. And then we're going to export it into our distributed data lake. Yeah. So that gets sort of saved in our distributed data lake. And we can bring that in later if we want. Finally, we're going to output into accumulate the this identity. This has like an identity. Basically just an index. It will usually be 0. The payload, right, which is just the thing that was essentially our transaction data. Right, we're not going to do anything with it. And our authorization output. We're going to encode that and pass it into accumulate, which is then going to decode it and set 3 storage items. So we're going to last info ID. We're going to put our ID in there. It's probably just going to be 0 because most of our work packages only have one thing in it. We're going to set the last payload to the payload and the last auth output to the auth output. Very easy. Yep. All right. Let's play with it. So here is our, I'm going to make this nice and big. Okay, here is our REPL, sort of CLI. Our CLI is essentially behind the scenes. This has a jam chain. It's a simple chain. I think it's got 6 validators with 2 cores. So the regular jam network, the production network, will have 1,023 validators and 341 cores. We don't need all of that on my laptop. So we're just going to have 2 cores and 6 validators. We can list the services. Jam starts with 1 service, or at least this testnet starts with 1 service, which is the bootstrap service. Why do we need a service? Like Ethereum didn't start with a smart contract in it. Well, Jam is quite pure. It doesn't have any particular code to do things like create services or transfer funds. Yeah? Like Ethereum does. If you send a transaction to the null address in Ethereum, it will create a smart contract for you. We don't have that equivalent in Jam. Jam is very pure. So if you start a jam system, if you make a jam network that has no services, you can't do anything, because the only thing you can do in jam is interact with services. If there are no services to interact with, you can't interact with jam. It doesn't make sense. So we always start jam with at least one service. And it's important that that one service, or those services between them, can provide you with the functionality you need to use jam to the degree that you want to use it. Now we've come up with a service that we call the Bootstrap service, which provides all of this sort of functionality. So you can create services with the Bootstrap service, transfer things, and so forth. Let's create a new service. So we're going to create a work package and send it to the Bootstrap service. This is all nicely packaged up for us in this REPL, all we are into a command called boot create service. And we're going to create the demo service that I mentioned here. So this is the demo service. It's already been compiled into some PVM code that happens to be residing at /demoservice.pvm. And we're going to give it some initial funds of a bit. We'll give it that much. Right, now, we've printed off a bit. What have we printed? Well, the first thing it says is null authorizer. There's no param, no token. The two are equal, so it's fine. So as you can see, this has created a work package that is now sending through jam. The first thing a work package does is it authorizes it, in this case using the null authorizer, and that's fine. The null authorizer is also, for what it's worth, another piece of code that has to be in the Genesis block of jam. If there are no authorizers, there's no way to authorize a work package. Yeah? Next, we have the we go into the Bootstrap service, right? This sort of Genesis service. And we're in the refine part. This is just coming. This message is coming from within the Bootstrap service. Next, the REPL is telling us it's guaranteed the work package and it's going to work its way on chain. So that's good. Going to the accumulate service, and the Bootstrap service's accumulate function is helpfully telling us that it's created a new service. And there you go. There's the ID of the new service. Now, when you create a new service, it's got to have new code. The code is stored in jam, somewhere in a service in jam. The service that you create's code is stored in the new service. You have to basically give jam that code separately, and it's doing that for us because we've got all of this automation on, so we don't have to think about this too much. The pre-image has been submitted, it's telling us, and everything is good. It's also switched, the REPL has a default service to avoid having to type this stuff out very often. We can list our services with ls, list services, and it tells us, yeah, we've now got two services, service 0 and service A, which is actually just short for this long 32-bit hex string. It's got this balance, it's got the code from the demo service PVM file. Okay, good. Let's try sending some work package into this new demo service. So we can do that by telling it we want to create a work item. When we create a work item, in fact, we can actually have a look. Let's ask it for help over work item. And it tells us, well, work item, you need to give it a payload and then potentially the service that it's going into, number of exports, amount of gas that you want to use, and so forth. For now, we will use the defaults. So we're just going to tell it the payload, and the payload will be hello Beijing. And okay, one item is pending. Now we need to feed this into jam. We do that with the guarantee. Command. And what this will do is it will take the pending work items, package them up into a work package, and send them off into jam. So there we go, and we're passing through the authorizer, refine, and accumulate. But now we have a different message for refine, because it's refine in the demo service. And it's telling us that it's got a payload, length 14, which is the length of hello Beijing. It's also telling us It's guaranteed this item, that's good, the work package, and it's got one export. We know what that export is, right? It's when we exported the string in the refine thing out into the data lake. So let's see if it's written to storage. Now let's go back to our code and check what the storage items that should have been written to are. So last payload and last auth output. We expect to see something. Let's read storage. Last payload. There we are. It's written hello Beijing into its storage. Let's look at the auth output. This is going to be not very interesting, I think, because it hasn't got an authorization string yet. Yeah. Auth equals, and then it's the empty string. There is no authorization token yet. We didn't bother setting one up. The default is just empty. Now we had one other thing, which is the index into the DA where we placed our message, and that was actually I can't remember what it was. It was last info ID. So we put some information string into the DA under this, and as expected, it's 0. Let's have a look and see. So we can list all of the segment trees, basically list the contents of the DA with LST or list segment trees. And sure enough, it's telling us that at block time t+4, at block 4, core 0, the work package OX70, whatever, has a segment root. This is the cryptographic commitment that we can use to reference the data that it exported. Gave an export. Index 0, 0, 0, payload, hello Beijing, auth output, auth is nothing. And then also, because the segments are 4K long, there's an extra 4,055 zeros at the end of it. And it also mentions that there's a proof page. This is part of the JAM protocol. Don't need to go into that too much. Okay, so this is demonstrating a few things. I want to demonstrate a few other things. First, let's try transferring some funds into this service and see what happens. So boot transfer allows us to transfer funds from the Bootstrap service into any other service. Let's ask for help on it, and it's mount and any sort of memo. So let's transfer 42 tokens with a memo, money for nothing. Okay, that looks like it's worked. So let's have a look and see what it should be doing. So when you transfer, in JAM, transferring a message and transferring tokens are the same thing. Sometimes you may only want to transfer a message and there'll be no tokens. Sometimes only tokens, there might be no message. In our case, we're doing a bit of both. So we print an info string, that's just a debug log. And then what we're going to do is make a message, which is just describing what the transfer is. Yeah. And then we're going to set a storage item, last-tx, into this message. So that means if we have a look at storage, let's do it again, read storage, and we want to look at the last transaction, last-tx, and see it should have some sort of message in telling us all about this transaction. And indeed it does. Transfer at block 7 from 0, which is the Genesis, the Genesis service, the Bootstrap service, to our new service, whose identifier is this E1, whatever string number, of 42 tokens with a memo, money for nothing. Now, so far, I've just been using the regular authorizer. Let's have a look. We can list the authorizers with list auths. And we have one authorizer. This is the default authorizer. It uses the null authorization code, and it's parameterized with the empty string. And then authorizers also come with the token, in this REPL, with a token that sort of makes them work. And in this case, the token is the empty string as well. And this together gives us a way of authorizing work packages. And all the work packages that we've made so far have used this authorization. Now we can make another authorization. That's easy enough. Push, we do it with push auth. Let's get some help to understand how we use this command. Push auth, authorizer code, host. Well, our authorizer code is the null authorizer, and the service which hosts this code is the Bootstrap service in 0. It's actually literally stored in the Bootstrap services storage. The code hash I happen to know is the hash of the Bootstrap code, which is a fixed constant. And then we can give it a parameter. At the moment, if I set these both to the empty string, it would be exactly the same authorizer as the one that we've got there. But let's try something a bit different. Let's set it to Beijing. Now, if I set these to different strings, it will fail because that little check in the authorizer that makes sure they're the same won't pass and it will panic. So let's set it with the same string and make it work. Okay, now it's happy, and if we list our authorizers, we now have 2. Yeah. Now, as it stands, if we send a work item, and there's a quick way of doing this, which is just guarantee work item, and I can change the code to like hello. This will then send it. Does exactly the same as what we did before, and it's, if you can see, the null authorizer is using the empty parameterization, this first one. It's not using our new one. Why not? Well, because, as I mentioned, the pool for core 0 is still the old authorizer, so it will use the old authorizer. We can look at the pool by inspecting pool. If we inspect pool of core 0, then it's this hash, which is, you'll see, equal to the original authorizer. Now what I can do is say, well, actually, I'm going to use the Bootstrap service again, and I'm going to assign to core 0 the new authorizer, 0x37, da da da. What this is doing is it's saying, in the future, you have to have an authorizer that is in line with this one in order to use this core. That prints off a big string, but it's okay. So if we now look at the authorizer, look at the pool, inspect pool of 0. Oh, it's still the old string. Yes. We haven't moved forward yet, so it's still on the old thing. All we've done is replace the queue. I mentioned very briefly that the queue is used to fill up the pool. Oh, inspect queue 0. And yes, the queue has the new hash, the new commitment. The pool doesn't. The pool's still working on the old commitment. Let's go forward a block, extend the chain, authored one block, and look at the pool now. Aha! It started coming into the queue has started filling up the pool with a new hash, the new authorizer commitment. If we go forward another 7 blocks, oops, oh, that's instruct. That was the wrong thing. Bollocks. Okay, let's very quickly do all of this. Where did we get to? Start a service and alter the assignment, and first push an authorizer, alter the assignment, and we should be back to where we were. Okay. Now, and extend the chain. 8 blocks. And look at our pool. Inspect pool 0. And yes. So our pool is now full of the new authorizer. It's not going to try and use the old authorizer anymore. So let's make a work item and guarantee it. We'll go back to hello Beijing. So we haven't done that yet on this instance. And see what happens. Ooh, is authorizer failed? Did I? Okay. Right. So let's instead do a work item and guarantee it on core 1. Good. And then guarantee on core 0. No workarounds pending. Guarantee on core 0. No workarounds failed. Okay. Well, anyway, I'm gonna end the demo there before I get further into this. I think I've taken your time enough. Thank you for listening.
Thank you so much, Gavin. Let's give him a big round of applause.